Hello everyone, this will be the exam review for exam 2. So this is the first lecture you probably ought to pay attention to. Alright, exam 2 is going to be Monday. When you get back from spring break, I'm going to post it at 11 a.m. and then it will be due back by 12 p.m. I'll probably add another 10-15 minutes to that on the due date just in case you need a little extra time. So I'll make it due at noon, but I'll add 15 minutes or so to the closing date for posting images. This will be a PDF file that you'll be able to download on Canvas. You can either print it or view it on screen. And then this will be due back just like a homework. So image files, those can be scans, those can be good quality cell phone pictures, or screen captures if you do it on your computer or on a tablet or something like that. So submission just like a homework. Open book, notes, lecture slides, calculator as usual for exams in this course. Topics will be velocity analysis, so focus primarily on identifying instant center locations and the number of instant centers for a mechanism. Velocity analysis using instant centers or vector loop analysis. Acceleration analysis will be more than likely cranked slider, since that's something you can do in an hour-long exam. So don't expect to see velocity analysis or acceleration analysis for fourbar just because of all those constants you have to calculate. And I'll go through this step by step. And then we have velocity analysis for velocity acceleration of any point too. Force analysis for a single link will be the last topic on there. Okay, so graphical velocity analysis, I haven't tested on this heavily in the past, but I left the slides in there for review. Just remember in this we can draw a scaled velocity vector for the velocity at point A. We know omega 2, we know the length A, we can find the magnitude. We use a scale factor. If it's 100 inches per second, we could use a scale factor of 1/100 to draw an inch-long vector on our page, just to fit things on the page. We find the direction of the velocity at point B being perpendicular to the position vector from O4 to B, and then we use the perpendicular of vector from A to B. That gives us the direction for the velocity at point B, and then we use these coordinates and our A velocity vector to find the magnitude of velocity B and the magnitude of the velocity B with respect to A. We can use that to find omega 3 by dividing the magnitude of the velocity of B with respect to A by B, and we can find omega 4 by the magnitude of velocity B, dividing it by C. We can then use that to find the velocity of point C. We take out the velocity of A. We need to add on the relative velocity of C with respect to A. We know that's going to be perpendicular to the position vector from A to C, so we draw a perpendicular there. And then we calculate the magnitude by taking omega 3, multiplying it by L, and then we get the velocity of C with respect to A. Add the vector velocity of A, so we add those two vectors, and we get the vector sum of the velocity of A and the velocity of C with respect to A. Instant centers. So there'll be several instant center questions, different combinations of things on the exam. First off is finding instant centers. So you should be familiar with using Kennedy's rule. I have a couple of samples that we'll do here in a second. Just remember for instant centers, the easy ones are between two bodies where they're connected at a revolute joint. So these two bodies are connected with a revolute joint here. That's going to be the instant center for those bodies 1 and 2. 2 and 3 is here. 3 and 4 is here. 4 and 1 is here. Excuse me. So the other instant centers, 2, 4, and 1, 3, we find using Kennedy's rule. So Kennedy's rule says any three bodies in planar motion will have 3 instant centers and they'll be on a straight line. And that is what we use to find 1, 3, and 2, 4. We can use a combination of bodies 1, 3, and 4. Those will have 3 instant centers, 1, 3, 3, 4, and 1, 4. We know where 1, 4 is at. We know where 3, 4 is at. Therefore, the one we don't know, 1, 3, has to be somewhere on a line formed by 1, 4, and 3, 4. We know 1, 2, and 3. We know where 1, 2 is at. We know where 2, 3 is at. 1, 3 is the one we want. So we find 1, 2. We find 2, 3. we draw a line formed by those 2 points. We know 1, 3 has to be on that line. So we know 1, 3 has to be on this line. It has to be on this line. There's only one intersection point between those lines. That's the instant center for 1, 3. We can do the same thing for 2, 4 with 2, 3, 4 and 1, 2, and 4. Those combinations of bodies will give us this line and this line. They'll intersect at IC2, 4. And I'll give some more examples here in a second. Number of instant centers, really all we need is this equation right here. We're looking for all of the order independent sets of two things from in-body. So we have an in-body mechanism. We're looking for all the different combinations of two links where the order doesn't matter. So that ends up being n times n minus 1 over 2. So for a 4-bar, this would be 4 times 4 minus 1 over 2. 4 times 3 over 2. This is going to be 6. So 12 over 2 gives us 6. The 6 instant centers we identified previously. For a crank slider, there's 4 bodies. There's 6 instant centers. For a cam follower, in this case, there's 3 bodies. There's going to be 3 instant centers, and so on. So I might ask a question for an 8-body mechanism, how many instant centers are there? You just need to calculate it using, let me get back to it, this equation. So that's pretty simple. So finding instant centers for an arbitrary mechanism, that will definitely be on this exam. So here's a few examples from previous final exams. So in this case, I give you the numbering scheme for the bodies and a few of the instant centers, and I ask you to find some. So I'll go through these for practice. So we want to find the instant center for 1, 5. So 1, 5, we're looking at, we're not given it, so it's not easy. So we need to use the other information we are given to find the instant center for 1, 5. So we're looking for combinations of bodies 1, 5, and something else. That's where Kennedy's rule comes in. So we look at the information we have and we try to figure out what other body in combination with 1 and 5 is going to give us something. So let's look at maybe 1, 5, and 6. Let's see what that gets us. So 1, 5, and 6. So 1, 5 is a question mark. We don't know where it's at. 1, 6, we know. 1, 6 is right there. 5, 6, 5, 6 is right there. So this looks pretty good. We know where 5, 6, and 1, 6 are. Therefore, 1, 5 has to be somewhere on a line formed by 1, 6, and 5, 6. So that's looking pretty good. Okay, 1, 5, and 4. Let's look at that. 1, 5, and 4. Let's look at that combination. So again, 1, 5, I don't know where it's at. 1, 4, I know it's 1, 4 is right here. 4, 5, 4, 5 is right there. I know that. So I know both of these things. So draw a line formed by the two I know. So I know that 1, 5 has to be on this line. It has to be on this line. Therefore, I see 1, 5 has to be right there. So that's the first part. Now I need to find 3, 5. So again, I'm going to take bodies 3 and 5 in a combination with another one. Now I'm guessing I probably need 1, 5 for this. So let's look at 1, 3, 5, that combination. So 1, 5 I know, right? It's right there. 1, 3 is given in this case. So I know that. And where did that come from? It came from Kennedy's rule. You'd use the other bodies to find 1, 3. But in this case, it's already given for you. So 3, 5, which is what I want. Where's that at? Well, I use 1, 5 and 1, 3. So draw a line from those points. And here's where my drawing skills are not going to help. So I know that 1, 5 and 1, 3 are on that line. 3, 5's got to be somewhere on that line. So I've got it narrowed down to that line. So I need some more information. We're given a lot of stuff about 3, 4 here. It's probably important. So let's look at 3, 4, 5. So 3, 4 is given. 3, 4 is between this slider and the link it's sliding with respect to. We know that's going to be perpendicular off at infinity land. So we know where that one is. It's off at infinity in that direction. 3, 5 is the one we want. So let's look at 4, 5. Do we know where 4, 5's at? Yes, we do. It's right here, so that's good. So the only one left is 3, 5, which is the one we want to find. So we know 4, 5 is here. We know 3, 4 is off at infinity land that way. Remember that since this is infinitely far away, I can look at any other point on this. So I could look at 3, 4 here, and that's still going to point off in that same direction to infinity to 3, 4. The same thing's going to happen here. We know the instant center 4, 5's here. We know that 3, 4 is still off at infinity in that direction. So I go from the point I know, which is 4, 5, point in the direction of the instant center 3, 4 that's off at infinity, and that forms my line here that 3, 5 has to be somewhere on. So 3, 5 has to be on this line, 3, 5 has to be on this line. They intersect right there. That's IC 3, 5, 3, 5, and I'm done. In this problem here, I want to know where IC 2, 5 is. We're given some information here. So same process. We're going to look at 2, 5, and some other body. So we're given a bunch of stuff here. So we're given 1, 5, right? So with 1, 5, let's look at 1, 2, 5. Let's look at that combination. All right, so that's going to be 1, 2, 1, 5, and 2, 5. All right, 1, 2 is not explicitly given, but we can find it real easily, right? So here is pivot 02. So the ground is going to be link 1. This is going to be link 2. This is 04, therefore this is going to be link 4. This is 06, therefore this is going to be link 6. That makes from this IC 4, 5 here, that means that the slider has to be link 5. And then that leaves 3. So this one's got to be link 3. So we can just go through the logic on this and number all these bodies without being given the numbers explicitly. So 1, 2 is going to be here. So we've got 1, 2. 1, 5 is given to be right here. We've got that. So draw a line. This is going to be bad. So draw a line from 1, 2 to 1, 5. Yep, I missed it completely, but let's say that that line goes through. I'll do a little better here, or at least I will attempt to. So we're going to draw a line from 1, 5 to 1, 2. 2, 5's got to be somewhere on that line. We're given 4, 5, so let's see if that makes any sense. So we're going to do 2, 4, and 5. So 2, 4 is given, right? 2, 4 is here, so we've got that. 4 or 5 is given, we've got that, so that'll let us narrow down the location of 2, 5. So 2, 4 is here, 4, 5 is off in infinity. Again, we know it's off there in infinity, so we can slide that down here and say that I 4, 5 is at infinity up in that same direction. So we take the point we know, and then we slide this down and point off in that same direction towards I 4, 5 at infinity. So we now have this line here. Oh, I didn't mean to do that. We have this line here, and then we have this line here, and that's going to be the intersection point. So we have 2, 4 and 4, 5 off in infinity. We have 1, 2 and 1, 5 here. Those are going to intersect at this point. That is where 2, 5 would be. So we'll use these two combinations of 3 bodies to find the location of 2, 5. Lastly, we'll do this example here. This is a Stevenson 6-bar. Again, we're given some stuff. We're given link numbering on this. We're given 1 instant center. This is a trivial instant center. We've already done that one before for 4 bars, 1, 3. So find 1, 5 is what we're looking for in this. So again, we're looking for 1, 5 and something else. So we're given 1, 3, so we probably ought to do 1, 5, 3. So 1, 3, we know. 1, 5 is what we want. 3, 5, do we know where that is? Yeah, 3, 5 is going to be where those things are pinned together, so we know that. So 1, 5, that's our question mark. So we know 1, 3 is here. We know 3, 5 is here. Draw a line between those 2 points. The one we don't know, 1, 5, has to be somewhere on that line. So that's good. Now we need 1, 5, and something else. I think 6. 6 looks good. So let's try that. So 1, 6, do we know where 1, 6 is at? That's going to be between the ground and link 6. It's going to be right there. So yes, we do know that. 5, 6, do we know where it's at? Yeah, those are pinned together there, so we know where that is. That leaves 1, 5 from this combination. So I've got 5, 6, and 1, 5. So 1, 6, 5, 6, draw a straight line between those. And 1, 5, the one we don't know, has to be on this line. It's got to be on this line. Therefore, that is where 1, 5 is at. So again, this is using the easy instant centers, which are the ones between 2 pin bodies, the ones on revolute or prismatic joints that are often infinity, perpendicular to the axis of the prismatic joint. We use that. We use Kennedy's rule. We can find any instant center we need. So the key is just finding a combination from the instant center you want, finding a combination of those 2 bodies and some other body that lets you, where you know 2 pieces of information, and you can use those 2 pieces of information to draw a line, and then use the line to narrow down the location of the instant center. Draw 2 lines, you've got the instant center figured out. Alright, velocity analysis for a 4-bar using instant center method. There's a lot of slides here, but what you really need to know for instant center for a 4-bar is skip all of this and this slide right here. All you need to do velocity analysis for a 4-bar using instant centers is use IC24, find it, which all you do is extend the coupler and the ground, and that will tell you where it is. And then you need this distance G and this distance H. The velocity ratio is the ratio of, I don't have it right here, this is G, this is H. So the velocity ratio is just simply the ratio of G to H. And that's something you can find all geometrically. So these equations here tell you how to find it in this example, but those were derived specifically for this example. If you had a situation where point A was on the inside here and point G was and 2, 4 was here, you'd have to set this up a little bit differently. So what I recommend is find IC24, and then just use whatever the simplest geometry to find G and H is. Don't just throw it into these equations and hope you get the answer, because these were derived specifically for this diagram. The main thing to know is find IC24, find G, which is the distance from O2 to IC24, and then find H, which is the distance from O4 to IC24. And then it's the ratio of G to H. You'll have to put a sign on this too. So in this case, if this link is moving this way, this link is moving this way, the velocity ratio would be positive. In the case where it's down in here, that would be different. If this is moving this way, this one would be moving this way, and that velocity ratio is negative. So you'll have to put the sign on the velocity ratio yourself. Torque ratio, inverse of velocity ratio, we talked about that. So if I asked for torque ratio for using instant centers, you'd use the velocity ratio. Sorry, you'd find the velocity ratio using instant centers, and then you'd invert that to find the torque ratio. Analytical velocity analysis, remember, is really easy for 4-bars. We just need these 2 equations and the position analysis that will be given on this exam, and we can find the velocity of the output link and coupler very simply. You can also turn this into velocity ratio equation by dividing both sides by omega 2, so I can have you find velocity ratio for a 4-bar without giving you the omega 2. Vector loop analysis, this is just an example here. Again, position analysis will be given to you, so all that's relevant here is plugging and chugging on omega 3 and omega 4, and this is the same problem that I previously solved with instant centers. We get the same answers within rounding. Velocity of points we can find too, if you need to find velocity of points. Crank slider, we've got the equations for omega 3 and d dot given the position analysis and omega 2. Those are just plug and chugs. Here's a sample here with position analysis done, but again, I'll give you the position analysis for the exam, so you won't need to do the position analysis. All you'll need to do is find omega 3 and d dot. Slider crank, only thing different here is we know d dot, you find omega 2, and then you go back to this equation, you go back to this equation and you can find omega 3 given omega 2. So crank slider, slider crank velocity analysis could certainly be on there. It's very easy to do. Velocity of any point, you can use the velocity for the S case, which is any point traveling on this link or any point traveling on the output link. You can use the P case to find the velocity of any point on a coupler, with an example here for both cases. Acceleration analysis. So fourbar is one of those things where we've got all of these constants. So that's position, this is velocity, here's this acceleration analysis coming here. And then these are the equations you need for acceleration analysis. It's just too much to do for a 1-hour exam. So you'll need it. I think you already did that for homework 6. So we've already covered it. I just really not going to do it on the exam because it takes too long to punch out all these constants. So don't expect fourbar acceleration analysis on the exam. Crank slider acceleration analysis will be on the exam more than likely. It ends up looking pretty simple. We've got the equation for alpha 3 given alpha 2 in the position and velocity analysis. So I could either give you the position and velocity analysis, or I could have you do both the velocity and acceleration analysis for a crank slider. I've done both. I can make some of these things simplify out, like if omega 3 is 0, you lose this whole term, you lose this whole term, and it gets easier. So I might do some things to help you out on that, but definitely something you can do in an hour exam. So for crank slider, given position velocity analysis, find acceleration, or given position, find velocity and acceleration for a crank slider. And then here's an example here that you can run through as an example case. Slider crank as opposed to crank slider, it's pretty easy. So in this case, we know D dot dot. We want to find alpha 2. We need to solve through this giant mess. I probably won't put that on the exam. It just takes too long. So expect crank slider velocity and acceleration analysis, not slider crank. Acceleration of any point, we get the S case for acceleration of any point on the input or output, or it'd be the crank of a crank slider. And then the P case for any point on the coupler for a fourbar, or the connecting rod for a crank slider. Force analysis, really the only thing you might see is single link. And for single link, it's all derived out for you. These are all just the equations of motion. And the only thing you'll have to do is the system matrix here. You'll need to put in these position vectors. You'll need to calculate m times a x, m times a y. If I give you a force P, put that in there. If I give you the weight, you can put the weight in there. And then this is just a plug and chug. So you won't have to rederive this matrix. I'll just have you set this up, and for a trivial case, solve it. And in this case, most of them will be trivial enough that you can solve this without using a 3x3 solver. You can just calculate it out by hand. So here's an example of that. Again, any exam type problem will be almost exactly the same as this example. So study this example. I will give you the omega, the alpha. I'll give you the force and the angle and the geometry here. You need to calculate your position vectors. So the position vector from the center of mass of 2 to where it connects to link 1, that's that position vector. Return the the weight into a vector, turn the force into a vector. Take the acceleration and break it into components, x and y. Find the position vector for where the weight is applied, and I'll probably give you something at 0, 90, 180, or 270 degrees just to make this something you can do in a reasonable amount of time. And then plug into the matrix. And then you can see this is very easy to solve without using a calculator or anything. This is just going to be this, right? Because there's 1 times that is that. 1 times that is that, and then given these two, you plug, so negative 58.3 times that plus negative 5.74 times that plus this is equal to 8.54. So it's real easy to take these two that you can solve for and go 208 times negative 58.3 plus negative 0.361 times negative 5.74 plus T21 equals 8.45. It's easy to solve for that T21 there. So that's something you can definitely do. You don't need a calculator or solver or anything for that. So I could have you give me the answers for this matrix, not just set it up, but solve for these components. So that's it as far as how many problems. There'll be an instant center identification problem. There'll be velocity analysis for a four-bar. There'll more than likely be velocity and acceleration analysis for crank slider, and then there'll be a single link force problem. So expect somewhere on the order of 4 to 5 problems. I'll add a little bit extra time for solving it. I'll put the due date at noon, but I'll leave the link open and won't assess any penalty as long as you get it submitted before the link closes. I'll be available for questions via email that time, it's same rules as the previous exam. I don't know. I mean, I really don't have a lot of control of what resources you do have, but again, I think I would just study for it the same way you study for the first exam. And you've got plenty of time between now and Monday, a week from Monday, to ask any questions. So that's it for the review, and I will get the exam posted on Monday when you get back from spring break. Have a good and safe spring break. Hopefully you're able to have some fun out there over this lockdown. Anyway, I will see you when you get back. Thank you.